Now, to look at a concrete setting, let's discuss the problem of designing a minimum jerk trajectory, which again makes sense if you have a third-order system. And let's assume that we're specified the starting position and the end position. Our functional is simply the integral of the square of the jerk, and we want to find the best x of t that minimizes this functional. We write down the Euler-Lagrange equations, and we see that a whole bunch of terms just disappear because they don't explicitly depend on x triple dot. What remains can be simplified into the sixth-order differential equation, which then can be solved analytically, and the result is this fifth-order polynomial in time. What remains is the subproblem of solving for the coefficients in this fifth-order polynomial. There are 6 such coefficients. In order to solve for these, you need to specify additional boundary conditions. We've assumed that we know the position at the start position and the end position. Now let's also assume that we know the velocities. And in this case, I've just assumed that these velocities are 0. In addition, let's assume we know the accelerations, and again assuming these accelerations are 0. The main goal of this exercise is to ensure that you have as many boundary conditions as the constants you're trying to solve for. Each of these boundary conditions gives you an equation. You can write down 6 equations in terms of the unknown constants and in terms of the known boundary conditions. Solving for these constants is now a linear problem. This is what the minimum jerk solution looks like. For this particular case, we've taken x starting from 0 and ending up at 1, taking a total of 50 time units. The velocity profile is bell-shaped, starting off with a 0 velocity, ending with a 0 velocity. It's unimodal, reaching a peak velocity in the middle. And the acceleration looks sinusoidal, again starting off with a 0 acceleration, reaching a peak acceleration, and then going all the way down to a peak deceleration, and then ending up at 0. This basic idea can be extended to multiple dimensions. If you're trying to generate trajectories in the xy plane, then you end up with 2 Euler-Lagrange equations. One for the x direction and one for the y direction. And here's how you might think about the minimum jerk trajectory in 3 dimensions. Here we're looking at a trajectory in the x, y, and theta space. We're assuming we're given a starting x and y position and a starting orientation theta, and we're given a final x, y, and theta. We're trying to find a trajectory that minimizes the functional that is given by x triple dot squared plus y triple dot squared plus theta triple dot squared. If I use the version of the Euler-Lagrange equations for multiple dimensions, I end up with a very straightforward solution. I essentially get 3 fifth-order polynomials, one in the x direction, one in the y direction, and one in the theta direction. By plugging in the boundary conditions, I get the plots that you see on the right-hand side. You see the starting position and orientation and the end position and orientation, and a smooth transition from the start to the end, and a velocity profile that is once again bell-shaped. It turns out that this particular problem is also relevant to modeling human manipulation tasks. This literature goes back to 1985 to a doctoral dissertation by Tamar Flash, and can be extended to multiple dimensions if you consider two-handed manipulation tasks. But we turn back now to our problem in robotics. In robotics, it's not sufficient to specify just the initial and final position and orientation. In order to ensure the trajectory is safe, you might want to specify intermediate waypoints. Instead of thinking simply about trajectories with known starting and end configurations, we want to think about trajectories that pass through intermediate waypoints. So let's consider the problem where you're given a set of intermediate time points and positions that you require the trajectory to pass through. So these time points are t0, t1, etc., and the corresponding positions are x0, x1, etc. In this case, we have assumed that there are m+1 time points and m+1 corresponding positions. A simple way to approach this is to define piecewise continuous trajectories, one for each time segment. The obvious way of doing it is to simply connect the waypoints. But this is not very practical. What if the system is a second-order system with inertia? Once you get started on the first segment, it's impossible for a second-order system to make the sharp turn at the kink. In order to make the trajectory more amenable to a second-order system, you want to insist that the trajectory is smooth and not have this kink that you see at the intermediate time points. To see how to solve this problem, let's look at a minimum acceleration curve for second-order systems. We look at the problem of solving for this function, x of t, but now the functional consists of many terms. Each term corresponds to a particular segment. From the Euler-Lagrange equations, if we solve this, we'll find that we get cubics for each segment. The resulting function or curve is called a cubic spline. So we now know the functional form of each segment. However, we don't have the constants. You'll see that there are 4 m constants for this cubic spline. Each of these constants corresponds to a degree of freedom. In order to determine these constants, we have to specify 4m different boundary conditions or intermediate conditions. Going back to our schematic, we're looking for a smooth curve. We know where these intermediate points are, and that gives us 2m boundary conditions. We further insist that the curve is smooth, more specifically differentiable up to 2 times at each of these intermediate points. That gives us an additional 2 times m-1 boundary conditions. And then finally, we insist that the curve starts with a specified velocity and ends with a specified velocity. In this case, that velocity is taken to be 0. That gives us an additional 2 boundary conditions. If I add these up, I get 4m constraints, allowing me to specify the 4m degrees of freedom associated with the undetermined constants. This basic idea can be generalized to nth-order systems. We have to specify appropriate boundary conditions in the beginning and in the end, and we have to specify intermediate boundary conditions. And these intermediate boundary conditions specify continuity up to the 2 times n-1th order derivative. This leads us to minimum snap trajectories where n is equal to 4. We're now ready to solve the motion planning problem for quadrotors using minimum snap trajectories.